So once we simplify our problem, if it's a situation in which we can use the uniform motion model, we should see a motion diagram that looks something like this. Our object can be thought of as a point, and we see that every velocity vector, which is what these green vectors are identical. Now, note that these were labeled over here to the left, but now, instead of thinking about a motion diagram, we can create a position versus time plot. Now, how do I know that this is a position versus time plot? Is that position is labeled on this vertical axis, and it's labeled with X, which represents horizontal motion, typically. Now, it's important to note that even though this is on the vertical axis, by labeling it X, that communicates the idea that it's horizontal motion. What goes on the horizontal axis in this situation is time. Now, for uniform motion, this plot will always be a straight line. Now, there are a few points that have been specifically labeled here, and those correspond to the points that have been drawn on our motion diagram. It's important to remember that that motion diagram does represent continuous motion, but we've only picked a few points. So similarly, our object is traveling continuously in space, but maybe we would only measure its position at very specific times. So now what we want to think about is how our speed, or our velocity, actually relates to the line we see here. And what we can say, what we've been saying before, is that our average velocity was equal to our displacement vector divided by time. What we can now say is that our velocity is equal to delta x over delta t. Now, one thing to be a little careful about here is I've actually called this the velocity vector, but you don't actually see a vector on the right side. Now, the reason for this is that we're talking about one-dimensional motion, and so I'm calling effectively this is the positive x hat direction, and so I could call this a vector, but since I know that it's one-dimensional motion, another way to deal with this would be to actually not have a vector on either side, but this could still be positive or negative, which would communicate its direction. So we look at the change in position, which is just one-dimensional right now, divided by the change in time. Now if you look, that's what's written here, but in particular, this is also equal to rise over run. So this is literally, mathematically, equal to the slope of this plot. So now here's what's important, is before when we were talking about motion diagrams, we said that this was only the average velocity. So what we can say, and this is going to be true only really for uniform motion, is that our velocity, which is constant, is going to be equal to our change in position divided by the corresponding change in time, which is equal to the slope. And what you should know from math is that the slope is the same of a straight line if you take this segment or you take a much larger segment. Or you could even take just a tiny little segment that is differentiably small and then think about the slope from a calculus point of view, which we will have to talk about when we talk about instantaneous velocity when we're not in uniform motion. So hopefully this makes some sense. Another way to think about this is that each time interval up here on the motion diagram, we actually had the same delta x. And that would make sense since we can also now write our equation as our change in position is equal to our speed in the x direction, I'll just label it, or velocity, times our delta t. And since we know that our delta t is the same on our motion diagram, and that this is now constant because we're in uniform motion, of course we will see the same change in position, the same delta x, every single time. So again, to just explain this briefly again, we've gone from our general motion diagram equation, which was for a vector, displacement, and velocity, potentially in two or more directions, and now we've simplified it a little bit by talking about one-dimensional motion, which is only in the direction of x, so we can actually drop the vector symbols and just think about it being positive or negative. We would still call that velocity if we're capturing that positive and negative information. So before we were looking at a position versus time plot. There weren't any numbers. We were talking about it in general. Now I'm looking at a velocity versus time plot. Note that there are numbers here, and since I have a quantity that's numerical, I must assign units to it. So this here is 2 meters per second. Now what you note is that on a velocity plot, we now see that our constant velocity is a horizontal straight line. So in this case, our velocity is going to be equal to 2 meters per second. It is always equal to 2 meters per second, which is why you have this horizontal line. It's important to note that I haven't actually said whether I'm working in X or Y, but we can assume that this is a one-dimensional situation. So that's what this initial plot shows us. Now, instead, if my velocity was down here, this now is equal to negative 2 meters per second. This is really important. This is what makes this effectively still be a vector, is that our direction is captured in that minus sign, that if we have a one-dimensional motion, we can define a positive direction to be, for instance, to the right, and negative to be to the left. However, it's still uniform in its velocity value over time. So this is still uniform motion. Now, one thing that I would like to mention, if we go back to some of those simplifying assumptions, that if this was me, for instance, walking backwards, I'm slightly clumsy, so I might stumble a little bit, and I might occasionally go a little bit faster and slower, and there's the natural pace of my gait. So if we were to measure my speed as I tried to walk backwards at a constant 2 meters per second, it wouldn't be a perfectly horizontal line. However, you really don't want to try to create a physics model for how Dr. Ackerman is klutzy. That's not the goal. So instead, we would ignore all of those fluctuations that have actually occurred in our data, and we would say that we can simplify this to be uniform motion of negative 2 meters per second. I'd like to introduce a few equations that are really important for once you're using a uniform motion situation. Now, these equations are only true if it's uniform motion, and I can't stress this enough. One of the most common mistakes that students make early on in this class is that they use these equations when you have acceleration. So uniform motion is only the case where velocity is constant, which by definition means acceleration is 0. So you must know when it's appropriate to use these, which is equivalent to knowing when it's appropriate to model your system as uniform motion. So when we use S like this just means, for instance, X or Y. We could be talking about a direction, for instance, along an inclined plane as well. So we have the same thing on both the V and our displacement. So you could imagine this as being written V sub X, so velocity in the X direction is equal to displacement in X divided by your time interval. So S is just a stand-in, for instance, for X or Y. So we can calculate our speed or our velocity, if you keep track of your signs, in direction S. Again, only in the case we have no acceleration is this true. And then similarly, we can actually calculate the position. Now here I'm going to say that this probably shouldn't be speed. I probably made a little bit of a mistake here. Let's call this velocity. And the reason we're going to call this velocity is that this should be positive or negative depending on your direction. And again, this equation could be written in a specific coordinate, for instance in the y direction, as our final value of y in y, our final position, is equal to our initial position in y, plus our velocity component in the y direction. Again, it does need to be positive or negative, multiplied by the time interval. Now, hopefully this isn't too confusing. Again, if you're unclear on what all of the subscripts or the symbols are, please make sure that you've gone back and watched some earlier videos. And again, these equations are only true if you have 0 acceleration. So uniform motion is only true if you don't need to worry about acceleration. It's important that you never just work with equations on their own, that you ignore the physical situation that they connect with. One of the best ways to connect equations with what the problem actually is about are these visual representations. So in this case, we're going to look at how that equation connects with this plot. So the final position is what's on the left side of the equation, and that corresponds to a specific time, and our initial position corresponds to literally our initial position. Now what's important to note here is that this isn't just equal to 0. We haven't started at an initial time of 0 and an initial position of 0. So sometimes these might be 0, but they also might not be. So that's part of why in this equation we have to specify the initial. That's also why we use a delta here, that this is the time interval. This isn't just the time value. So if you had written t final here, this would be incorrect since it needs to be this length of time, and we didn't start at an initial time of 0. So then, one of the things you can think about here of why this equation makes sense is that we said that our velocity in coordinate s, where again that could be x or y, is going to be equal to the change of that component, so the displacement, divided by delta t. So let's just see what happens if I literally plug this in here. This now would say that our final position is equal to our initial position plus change in position over delta t times delta t. Well, you can think of this as delta t over 1, so this delta t and that delta t cancels. So in the end, we just say that our final position is equal to our initial position plus our change in position. Now if I subtract s sub I from both sides, I now have that final position minus initial position equals delta s. This is literally the definition of what change in position means. So this is a fairly simple equation that again is only valid if you have uniform motion. But the other thing to realize is that it's true for any value of initial and final times and positions. So we can actually write this in a slightly different way, where we say that I'm going to have some position that is a function of time is equal to my initial position plus my velocity times time. Now I am going to call this delta t here, but in this case this is kind of a continuous variable, that whatever point I want in time could correspond to the delta time here. Again, you wouldn't just want to call this t, this is t final minus t initial, so we could write this in a little more clear manner. So instead of saying delta t, I can say t as a continuous variable minus my t initial, because this wasn't in fact 0 in this situation. So now for any value of t, you plug that in, and you get a different value of position. And that in fact is what's corresponding to starting here and moving along this straight line. So this is just an equation for a straight line. So again, it's really important to recognize that you only have uniform motion if you have a straight line in position versus time, the slope of which is corresponding to your velocity, and make sure when you're using these equations that you're careful about the difference between these deltas, these change, and our initial and our final.